Welcome, this is Professor Ridge, and today's lesson 9.1, Sequences and Their Notations. Today's first learning objective, write the terms of a sequence defined by an explicit formula. One way to describe an ordered list of numbers is a sequence. A sequence is a function whose domain is a subset of counting numbers. Okay, so that's an important detail right there. So the domain is a subset of the counting numbers. Okay, counting numbers or natural numbers. And if you remember what that is, right, that's the set 1, 2, the numbers you use to count. 1, 2, 3, 4, so on. Okay, so the ellipsis indicates sequence continues indefinitely. Each term in the sequence is called a term. Each number in the sequence is called a term. Okay, the first 5 terms of this sequence are 2, 4, 8, 16, and 32. Okay, so let's talk about some notation here. So typically we define like a sequence. We can, if we call it sequence A, the subscript says what term of the sequence is, and it's also the input value from the domain if we're going to create an explicit formula. So the first, so if I call this sequence A is equal to A sub 1, A sub 2, A sub 3, A sub 4, so on. And if I can describe a way, a formula that can represent this sequence in terms of so the input value. So if you're the first term, so we read this A sub 1 as the first term. So A sub 1 in this case is 2, 8, and then the second term, that's A sub 2, which in this case is 4. The third term, A sub 3, is 8. And then the fourth term, A sub 4 is, what is it, 16? And then we'll stop at the fifth term here. Fifth term is A sub 5, which is 32. Now, if you can figure out a formula, an explicit formula, if you notice, okay, you see this pattern, it's doubling every time. So if this is 2 to the first, so if you're multiplying by 2, multiplying by 2, multiplying by 2, right, you're going to get powers. 2 times 2 is 4, so that's 2 squared. And then once you recognize that, then you can say, oh, okay, I can get an explicit formula for the, what we say, the nth term. So the nth term, well, I guess I should finish this one, to the 5th. Let me write that a little better, 2 to the 5th. Okay, the nth term, A sub n, is equal to 2 to the nth power. This is what we call an explicit formula for the sequence. And we call this the nth term or the general term of the sequence A. Okay, so either of those. And again, this is what we would call an explicit formula, because we're explicitly stating, here's how you get the nth term. You take 2 to the nth power. Okay, and I just want to highlight a couple of definitions here in the text. So basically, so that sequence we're just doing, since we can explicitly state the nth terms to the n, you can write the sequence as follows: 2, 4, 8, 16, 32, ... so and so on, and then comma 2 to the n, comma ... So basically this is going to continue indefinitely, and a sequence that continues indefinitely, right? If it continues indefinitely, oops, let me try that again. So if it continues indefinitely, we call it an infinite sequence, right? It goes on forever and ever and ever, right? So the domain of an infinite sequence is a set of counting numbers. So remember, that's important. The input values is going to be just 1, 2, 3, 4, so on to infinity, right? If we consider only the first 10 terms of the sequence, so you stop at the 10th term, this is called a finite. So if you stop somewhere, that's finite. So infinite goes on forever, finite stops. There's a fixed number of them. All right, and here's just basically the formal definition sequence. A sequence is a function whose domain is the set of positive integers. That's the same thing as saying the natural numbers or the counting numbers. So 1, 2, 3, 4, so on. A finite sequence is a sequence whose domain consists of only the first n positive integers. So you're going to stop somewhere, like the first 10. The numbers in the sequence are called terms. Okay, so a sub 1 is the first term, a sub 2 is the second term, so on. The variable a with a number subscript is used to represent the terms in the sequence and to indicate the position of the term in the sequence. And also tells you, like if you do an explicit formula, that tells you what the input value is. We call a sub 1 the first term, a sub 2 the second term. Okay, I mentioned this before, but it's worth repeating. A sub 3 is the third term of the sequence, so on. The term a sub n is called the nth term of the sequence, or the general term of the sequence. An explicit formula defines the nth term of a sequence using the position of the term. A sequence, so again, that's kind of what, like we just did, 2 to the n. That would describe a sub n is equal to 2 to the n. So that's an explicit formula. And a sequence that continues indefinitely is called an infinite sequence. Okay, so make sure you understand these terms, key terms. Okay, example 1, writing the term sequence defined by an explicit formula. Write the first 5 terms of sequence defined by the explicit formula a sub n equals negative 3n plus 8. So basically what I tell my students, just think of this as like an alternate function notation. So if we did f of n is equal to negative 3n plus 8, then most students don't have a trouble doing this. You know, we're pretty comfortable with this function notation. We just change this to really remind you that, hey, this is not a normal function where the input values are all real numbers. Remember, for a sequence, the input values are just the integer, positive integers, the counting numbers. So you can only put in 1, 2, 3, so on. And because it's a sequence, we typically do it in order, and we list the output values of the sequence. So a sub 1, which is the first term, would be negative 3 times 1 plus 8. So negative 3 plus 8 is 5. A sub 2, negative 3 times 2 plus 8, which is negative 6 plus 8. A sub 3 plus 8 is negative 9 plus 8, which is negative 1. A sub 4 is negative 3 times 4 plus 8, which is negative 12 plus 8, which is negative 4. And also, if you see the pattern, you can kind of bypass this and just, you're subtracting 3. That's what this times 3 is doing. This times negative 3. We're going to be subtracting 3. And we'll talk about that in a later section. Okay, so negative 15 plus 8 is negative 7. So our first 5 term sequence would be 5, 2, negative 1, negative 4, negative 7, then so on. Okay, investigating alternating sequences. Sometimes sequences have terms that alternate. We're talking about the sign. They actually alternate in sign. The steps to finding terms sequence are the same as if the signs did not alternate. However, the resulting terms will not show increase or decrease as n increases. So let's take the following sequence: 2, negative 4, 6, negative 8. Notice the first term is greater than the second term is less than the third term, and the third term is greater than the fourth term, so it alternates. That trend continues forever. Do not rearrange terms in numerical order to interpret the sequence. Writing the terms of alternating sequence defined by an explicit formula. Write the first 5 terms of the sequence. Okay, so typically the way you get terms to alternate sign is this negative 1 to the n. So just want to point out, if you do negative 1 to the n, if you do it to the first power, that's negative 1. Second power, negative 1 times negative 1 would be positive 1. Negative 1 to the third power will be negative 1 times negative 1 times negative 1 will be negative 1. So basically, if this is even, let me write it here. So if negative 1 to the even, I'll just write even up here, that's going to be equal to 1. Negative 1 to an odd will equal to negative 1. Okay, so then it's going to alternate positive, negative, or negative, positive, negative, positive. Okay, so this is what's creating the alternating sign. So if we want to find the first 5 terms, again, remember, we're going to start with 1. That would be your input value for n. So we get negative 1 times 1 squared is 1 over 2, so that's negative 1/2. Now a sub 2 will be negative 1 squared, 2 squared over 2 plus 1. So that would be positive 1 times 4 over 3, which is 4/3. Now a sub 3 would be negative 1 cubed, so that would give us a negative 1. Let's see, n is 3 squared over 3 plus 1. So that would be a negative 1 times 9 over 4. So negative 9/4. Then a sub 4 will be negative 1 to the 4th times 4 squared over 4 plus 1. So that'll give us positive 1. 4 squared 16 over 5. So we get 16/5. And then the 5th term, we get negative 1 to the 5th times 5 squared over 5 plus 1, which is negative 1 times 25 over 6. Okay, so our sequence, negative 1/2, 4/3, negative 9/4, and then what's the next one? 16/5, negative 25/6, so on. There you go. Okay, investigating piecewise explicit formulas. So we learned the sequences are functions whose domain is over the positive integers. This is true for other types of functions, including some piecewise functions. Recall that a piecewise function is a function divided defined by multiple subsections if a different formula might represent each individual subsection. So taking a look at example 3, write in terms of sequence defined by a piecewise explicit formula. Write the first 6 terms of the sequence. So we have 2 different formulas or explicit formulas for the terms depending on, here's the condition. So if n is not divisible by 3, we're going to use n squared. If n is divisible by 3, you're going to use n divided by 3. Okay, so if you can get a whole number when you divide by 3, then you're going to divide it by 3. If not, you're going to square it, right? So there's 2 cases depending on what the input value is. So what are numbers divisible by 3? So let's kind of think about that. Numbers divisible by 3 are 3, 6, basically the multiples of 3. So 9, 12, because 3 divided by 3 is 1, 6 divided by 3 is 2, so on. Right? So basically just your multiples of 3. So 1 is not divisible by 3, so we're going to use n squared. So we do 1 squared, which is 1. 2 is not divisible by 3, so we do 2 squared, which is 4. Now 3 is divisible by 3, so we're going to use the bottom case, 3 divided by 3, which gets us 1. This would be an extremely hard sequence to figure out the pattern for if you just give in a few terms. Let's see. Next one, a sub 4. 4 is not divisible by 3, so we're going to use n squared. Is 16. 5 is not divisible by 3, so we're going to do 5 squared. It's 25. 6 is divisible by 3, so we're going to go 6 divided by 3 and get 2. So our sequence, first 6 terms would be 1, 4, 1, 16, 25, 2, so on. Okay, so now let's work the other way. If we have the sequence, let's find the explicit formula if we can recognize the pattern. So first, you're going to look for the pattern. If the terms are fractions, look to separate the pattern among numerators and denominators. So that's a common trick. Sometimes you can see a pattern in the numerator and then a different pattern in the denominator, and then you can think of those as separate. Look for a pattern among signs, see if it alternates. Write a formula a sub n in terms of n. Test your formula for n is 1, 2, and 3. All right. So there's a couple of tricks that you learn along the way, but basically you just look for a pattern. So the first one here, look at its fractions. So let's look at the numerator and denominator separately. And then another trick is sometimes if you have fractions, you want to, what I say is unreduce them. So if it's reduced, it makes it hard to see a pattern. Okay, so we don't have any problems here. They're all doesn't look like any of these were reduced. So if you look at the top, you got 2, 3, 4, 5, 6. So if I can think of it now, if I separate the top, if I have 2, and I'm ignoring the sign for right now, 3, 4, 5, 6. See, that's going to be one more than the term you're on. So the top number is going to be n plus 1. Now the bottom number is 11, 13, 15. So it's increasing by 2 every time. So that's going to be, let's see, 11, 13, 15, 17, 19. That's increasing by 2, so I know it's going to be plus 2, plus 2 plus 2. And then I need to start at 11. So basically, if you're adding 2, adding 2, adding 2, you're going to do 2 in. Okay, so if I put in 1, that gets me at 2, but I need to scale it to 11. So if you do 11 minus 2, that's 9. Not scale it, I need to slide it, right? Shift it. So if I put in 1, that's going to give me 11. If I put in 2, that'll get me 13. Put in 3, that would get me 15. So that's going to work. So 2n plus 9. Now to alternate negative, positive, we're going to times that by negative 1 to the n. And then that'll be our formula. And you can check if you put in 1. If you put in 1, you get negative 1. So if n is 1, you get negative 1 to the 1 times 1 plus 1 over 2 times 1 plus 9, which would get us negative 1, 2 over 2 plus is 11. Right? Now if I put in 2, negative 1 squared, 2 plus 1, 2 times 2 plus 9, you can see you get 3. Okay, this would be positive 1. Then 3. 4 plus 9 is 13. Okay, and then if you check 3, that one will work as well. Okay, let me erase all this. All right, so that's A. Now B, let's look at B here. So the top stays the same, so that makes it easy. So for B, A sub n, so the top's just going to be 2. So no changing there. Negative, 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 so that doesn't change. So we got that. Now the bottom is 25, which hopefully you're thinking 5 squared, and then this is 5 cubed, 5 to the 4th. So you just have to be able to recognize the pattern there. And there's no trick. There's some tricks, but it takes more practice basically, just seeing them. So, but this is starting at 5 squared, right? And then the next one is negative 2 over 5 cubed, and this is for n is 1, 2. So see how that's off. You have to add 1 to whatever n you're on. Add 1. So that's going to be the formula. Will be negative 2 over 5 to the n plus 1. Okay. And then this one, notice they all have e, so that's not changing. So that's just going to be e, and then the top is starting at 4 and it's increasing by 1. So that's just going to be n plus, and then you got to shift it so you start at 4 instead of 1. So that's going to be n plus 3 to shift it to start at 4. So 4, 5, 6, so on. Okay. Write the terms of the sequence defined by a recursive formula. Okay, so that's our next learning objective. So a recursive formula is a formula that defines each term of a sequence using preceding terms. Recursive formulas must always state the initial term or terms of the sequence. Okay, so this is a common way of defining sequences is you start out the sequence and then say what do you do to that term to get to the next term, or what do you do to the previous 2 terms to get the term you're on, right? All right, example 5, writing the terms of sequence defined by recursive formula. So write the first 5 terms of the sequence defined by the recursive formula. So again, we start out with, they have to tell us what the first term is, or initial term. And then they're saying that to get the nth term, you take 3 times this n minus 1, you read it as the term before it. and then subtract 20. So just to kind of think, if here's n is 1, 2, 3, so on, at some point you're going to get n. The term before it would be n minus 1. The term after it would be n plus 1. Okay? So you kind of think of a relationship here. If you want the term before n minus 1, that would be n minus 2. If I want the term after n plus 1, it would be n plus 2. So these are what we call consecutive terms. So if I want to find the nth term, I have to look at the term before it and multiply it by 3. That's what this tells us. The term before it, the preceding term. Okay, so a sub 2 will be 3 times a sub 1 minus 20, which is 3 times 9 minus 20, which is 7. Okay, a sub 3 would be 3 times a sub 2 minus 20. A sub 2 is 7, which is 21 minus 20, which is 1. A sub 4, let me write a sub 4 over here. A sub 4 would be 3 times a sub 3 minus 20, which equals 3 times 1 minus 20, which is negative 17. Okay, and then a sub 5 would be 3 times a sub 4 minus 20. For some reason I feel like I did something wrong, but I'll check in a minute. 3 times negative 17 minus 20. Let's just double check this. So we got 9. 27 minus 20 is 7. 21 minus 20 is 1. 3 minus 20 is negative 17. Okay, what's this? Negative, let's see, 21, 51 minus 20 would be negative 71. Okay, so the first 5 terms of that sequence is 9, 7, 1, negative 17. I don't know why. It just didn't feel right. Okay, so that hopefully that's right. And checking the book, let's see. 971, negative 17, negative 71. Yep, that's right. Okay. Let's go to the next problem. Okay, so example 6, write the first 6 term sequence defined by the recursive formula. So here they give you 2 initial ones, first term, second term, and then for all the preceding terms or subsequent terms, you take the 2 previous terms, you take the one that's right before it times 3, the one that's 2 before it, right? And times it by 4. So a sub 3 will be 3 times the one right before it, a sub 2, plus 4 times the one before that one, which is a sub 1. That's why you have to be given the 2 initial ones. So that would be 3 times 1 plus 4 times 2, which equals 3 plus 8 is 11. A sub 4 is 3 times a sub 3 plus 4 times a sub 2, which is 3 times 11. Oh, I guess I did this backwards. This should have been 2, and this should have been 1. I just caught that, so it's going to change my outcome here. So 6 plus 4 is 10. Okay, so a sub 2, so you do 3 times the one before it and 4 times the one 2 before it. So this would be 10 plus 4 times 2. So it'll be 30 plus 8, which is 38. A sub 5 is 3 times a sub 4 plus 4 times a sub 3. A sub 4 is 38. A sub 3 is 10. So let's see here. Get my cheapy calculator that's built into this note program. 3 times 38 plus 40. 4 times 10, 40. So 154. And then the last one that they asked us to do, so 3 times the one before it, a sub 5, plus 4 times the one before that one, so a sub 4. So we get 3 times 154 plus 4 times 38 equals, so let's see, 3 times 154 plus 4 times 38 equals 614. So you can see this starting to grow pretty big. So our sequence, first 6 terms, 1, 2, 10, 38, 154, and 614. Okay, the last learning objective, use factorial notation. Okay, so in factorial is a mathematical operation that can be defined using a recursive formula. N factorial of n, denoted n with the exclamation point, is defined for a positive integer n as 0 factorial is 1. Okay, that's a special case, so it's just defined that way. 1 factorial is 1. N factorial is you start at n times n minus 1 times n minus 2, so on, times 2 times 1 until you get to 1. Okay? So if I wanted to do 5 factorial, you start with 5 and then you go down 4, 3, 2, 1. And then type that in your calculator. Some calculators have the factorial button. Let's see if Desmos has it. Yeah, so just the exclamation point. You can probably just type it too with your keyboard, the exclamation point. Let me try that. Okay, and it's 120. So 5 times 4 times 3, 5 times 4 times 3 times 2 times 1. And you see it's 120. Okay? Example 7, write in term sequence using factorials. Write the first 5 terms sequence defined by the explicit formula a sub n equals 5 times n divided by n plus 2 in parentheses, factorial. Alright, so the first term will be 5 times 1 over 1 plus 2 factorial. So that's 5 over 3 factorial. 3 factorial is 3 times 2 times 1, or 6. So you get 5, 6. 2. So we're going to get 5 times 2 over 2 plus 2 factorial, which is 10 over 4 factorial. So 10 over, so 6 times 4 would be 24. And then we reduce this, so if you divide 2 out of there, you get 5 twelfths. 3, you get 5 times 3 over what? 3 plus 2 factorial, which is 5 times 3 over 5 factorial. Now what I like to do, Notice I didn't multiply this because I want to cancel, right? So 5 times 4 times 3 times 2 times 1. The 5's cancel. The 3's cancel. That leaves me 1 on top. And then that leaves me 4 times 2, which is 8. Okay? And then the fourth term, let's see, the fourth term would be 5 times 4 over 4 plus 2 factorial. Again, I'm not going to multiply it because I'm going to reduce. 4 is 6 factorial. 4 plus 2 is 6 factorial, which gets me 6 times 5 times 4 times 3 times 2 times 1. So the 5 and the 4 cancel. So I get 6 times 6, which gets me 1 over 36. And then finally, 5 times 5 over 5 plus 2 factorial. Again, I'm not going to multiply this because I'm going to cancel. So that'd be 7 factorial. I don't know why I wrote it way over there, but anyway, 5 times 5, 7 times 6 times 5 times 4 times 3 times 2 times 1. So just 1 5 cancels. And we get 5 over, let's see here. So that was, let's just use my calculator. So we got 7 times 6. Oops. Let me start over. 7 times 6 times 4 times 3 times 2. You don't have to do the times 1. So that's 1,008. Okay, so our sequence will be 5 6, 5 12ths, 1 8th, 1 8th, 1 over 36. Sometimes you don't reduce it because if you're trying to recognize the pattern, you can't see the pattern when it's reduced. But typically, when you represent the final answer, you want to reduce the fractions. Okay, so that brings us to the end of that section. So again, practice, practice, practice. Go to the end of the section, do the exercise set there, all the odds at least, and then as many as you feel necessary beyond that. All right, have a great day. Talk to you next time.